The next type of energy that we want to talk about is going to be kinetic energy, which I've already said is going to be the energy of moving things. So if something is moving, then it has something called kinetic energy. Much like potential energy, it's going to have the same unit of energy, which is going to be a J for joule. Now, how do we go ahead and calculate it? Well, the kinetic energy, that's going to be this Ke right here, is simply going to be 1/2 multiplied by the mass multiplied by the velocity multiplied by the velocity, or we could kind of shorthand this to say 1/2 mass velocity squared. Now, this is kind of interesting because if you think about doubling the speed of an object, then the kinetic energy is going to essentially go up by a factor of 4, and we can kind of prove this to ourselves. Suppose we said that our mass was 1 and our speed was 1, so mass is equal to 1 and the speed is equal to 1, and the kinetic energy is going to be 1/2 times 1 times 1 squared, so half of a joule. Now what happens if we were to double the velocity, so the speed is equal to 2, right? 2 is double 1. Then the kinetic energy is simply going to be equal to 1/2 times 1 times 2 squared, which is going to be equal to 2 joules, and that is 4 times as large as this guy right here. Now let's just do a quick little calculation about how much energy a 50 kilogram runner going 2 meters per second or 5 miles per hour is going to have. Recall that kinetic energy is simply going to be 1/2 times the mass times the speed squared. So that's going to be a 1/2 times the mass, which is 50, times 2 squared. So it's going to be 100 joules is equal to the kinetic energy. Now, how does an object gain kinetic energy? Let's just kind of think about your car, and it's sitting there at a stoplight. So it's got a speed equal to 0, and then you stomp on the gas pedal, and at some later time you've got a speed maybe of 10 meters per second, right? Then what we can kind of say is, well, we had to do some work. So if you do work to an object, then it's going to gain kinetic energy, much like when we did work to a stone and tried to lift the stone up right here, then it gained potential energy. Same thing. We're applying some force over some distance, right? Your car is applying some force over some distance right there, and that's going to all turn into, in this case, 1/2 mass speed squared. Now, one thing about energy is that it's going to be what we call a conserved quantity, and this is going to be very, 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 very important, so you definitely want to star this. We'll be saying that energy is conserved for, well, a very long time. When I say energy is conserved, what I mean is it may slosh from one form to another form, but it's never going to go away. It's never going to be created. So let me just think about, just for a second, the total mechanical energy, which is going to be the sum of the potential energy plus the kinetic energy. And let's think about a roller coaster. And here we have a roller coaster right here at part A, and here it's going to be at B, and here's going to be at C, and here it's going to be at D, and right here E. Now, the total mechanical energy, the sum of the potential energy plus the kinetic energy, is going to be a constant number. Now, right here at point A, perhaps all of the energy is in the form of potential energy. Right over, and let's just for the sake of argument say that it's equal to 100 joules. Then as this roller coaster goes down here, now it's going to have some potential energy plus kinetic energy, right? It still has a little bit of height, but now it definitely has speed. So maybe it has 70 joules of kinetic and 30 joules of potential. Still, they add up to the mechanical energy of the system of 100 joules, and then the roller coaster goes up the hill, and now maybe it has 70 joules of potential and 30 joules of kinetic. What that kind of means is, well, the amount of kinetic tells you how fast it is going. So here it's going relatively fast compared to right here. Right over here, still, potential energy plus the kinetic is going to be equal to 100 joules. And then right down here, all of the energy is in kinetic energy, and the amount of kinetic energy is going to be 100 joules. And what that means is here it's got 100 joules, and so it's going very fast. Right over here it's going fairly slow. Right over here it's going somewhat fast. And right over here it's not moving, so no speed. Now I have a nice little fun demonstration for you where your favorite physics professor is going to essentially take a big heavy ball and tie it to the ceiling, and he's going to release it, and it's going to swing just like that, and then it's going to swing back, and he is not afraid because the amount of potential energy that it has right here, the height that it has, is going to be some number. And so what he does is he knows that it's going to swing down right here, and here it's going to have, some kinetic energy, potential energy. The potential energy that it has is going to be the same as it was right there, and it's going to swing all the way back, and it's never going to go higher. It's never going to have more potential energy than it initially had, and so it's not going to touch his chin. Let's just take a quick look at energy in this Java simulation right here. So here I've kind of got my proverbial skateboarder, and you can kind of see that I'm affecting his potential energy by moving him up and down. And so I'm just going to kind of set him right here and take a look at his total energy. It's never going to change. It's going to flow between potential energy and kinetic energy. And he has the most potential energy at the top right here, and he's going to have the most kinetic energy at the bottom. The other type of energy that I'll talk about in a little bit is going to be thermal energy. Now, I'm not going to harp on this too much longer, but energy is a conserved process. If you think about having a big hunk of metal up here, and it has a whole bunch of potential energy, then if you were to go ahead and cut this string right here, then obviously it's going to fall down, and it's going to gain speed, and all of the potential energy that it had right up here is going to flow into kinetic energy. So if it had 50 joules worth of potential energy, then it's going to go into 50 joules of kinetic energy. It's never going to be like, 60 joules or something like that. That's never going to happen. So what the conservation of energy says is the energy that this cart has right here is going to be the same energy that the cart has way down here when I release. So let's just kind of do a quick little practice here of energy flowing from one form to another. Suppose your car is at rest at the top of a 100-meter hill. So I'm going to do one of these numbers right here, and so we have some height right here, so we're going to have some potential energy, and then the car is going to go down the hill, and it's going to get some potential or some kinetic energy, so it's all going to turn into speed. And what we're going to do is we're going to say the potential energy at the very tippy top is going to be equal to the kinetic energy that it gains. So what we're going to do is we're going to say mass times gravity times height is equal to 1/2 mass speed squared. And something that's kind of interesting but not surprising is that the mass is going to go away. And then what we can do is we can say, well, I want to get rid of that 1/2, so I'm going to multiply this side by 2. And if I do that, I have to multiply this side by 2. So those guys cancel out. Then I kind of have a 2gh is equal to speed squared. And for lack of a better word, if I want to get rid of that square, I need to take the square root of both sides. So I'm left with the speed is equal to the square root of 2 times g times h. So that's going to be equal to the square root of 2 times 10 times 100, which is going to give us a speed that is about 44.7 meters per second, and that's actually really fast. We would have to worry about air resistance. We're actually not too awful surprised that mass went away right here, because we do know that the mass doesn't matter for falling objects, so it's not surprising that it goes away. So this kind of leads us to something called the WorkEnergy theorem that essentially says, if you gain or lose energy, then it's going to be because work was done. Remember, work is kind of the flow of energy. And if we were just talking about kinetic energy, then the work you do is going to be equal to the change in kinetic energy. So kind of a 1/2 mass speed squared, if you will. And what this kind of says is we know that if you double the speed of an object, then the kinetic energy is going to go up by a factor of 4. I kind of showed that earlier. What that says is if you double the speed of an object, then it's going to take 4 times the work. Now, this applies to cars speeding up, but it does also apply to slowing down as well. I mean, if a car is going like that and it's got some kinetic energy, then if you want to reduce that kinetic energy, then you need to take some of that energy away. And where does that go? Well, there's some frictional force that's applied by the brakes, multiplied by some distance, and not surprisingly, the work is actually going to work itself out to be negative because, well, you're taking the energy away. Now, where does the energy go in the previous example where we had the car on the cliff? Well, you've already said the energy is not going to just go into the ether. The energy is going to go into thermal energy. It's going to go into heating your brakes up. And that's kind of why when you drive down a big hill, say Mount Washington or something like that, then they actually have people that essentially stop you and check the temperature of your brake pads just to make sure you're not overheating them as you go down big heavy hills. And I have a nice little demo on this as well. So in this example, I have a bowling ball. I'm going to do some work to it. It gets gravitational potential energy. I drop it. Gravity does some work to it. It gets kinetic energy. Then where does that energy go? Well, it goes into hitting the silly putty and warming it up. So now we can kind of generalize the work-energy theorem to just very briefly discuss the conservation of all energy. And essentially, energy cannot be created nor destroyed. That's what I mean when I say created. It can be transformed or sloshed from one form to the other, but the total amount is never going to change. When we transfer energy, we're actually doing something called work. So if we considered a system like this, and we said, okay, well, I'm going to do some work to this system, and I'm going to go ahead and I'm going to pull this pulley up, then I'm doing some work, and what I'm doing is I'm gaining potential energy. So right over here, I had no energy, I did some work to it, and I gained some potential energy. If we were to kind of release this guy and let this guy fall down to the ground, then the potential energy that we had right here is going to slosh into kinetic energy. So right here we have our work, and here we have energy, and here we have energy. So just take a second and think about what you would choose for this guy. You have a potential energy of a drawn bow, right? That's some stored energy waiting to do something, and that's 50 joules. And we measure the speed of the arrow after it's been shot, and it turns out that it only has 40 joules of kinetic energy. So, kind of what's the deal right here? Is energy not conserved? No, energy is always going to be conserved. The question is where does it go? Obviously, I wouldn't be too happy if you chose that guy. And where it actually goes to is warming the bow up. Why? Well, if you think about it right here, that's the energy after it left the bow. It hasn't even hit the target yet. So 10 joules have gone to warming up the bow. Let's just talk for just a little bit about kinetic energy and momentum. I don't really want you to confuse them. They're similar in that both are properties of moving things, but they are very, very, very different. Momentum is a vector quantity, right? And it's going to be mass multiplied by velocity. So it has direction, and it can, cancel out. It can be negative. Kinetic energy, on the other hand, is a scalar, and just for reference, 1/2 mass speed squared. It's a scalar quantity, and it can never be canceled, and it can never be negative. They both do depend on velocity, but momentum kind of goes like velocity, and kinetic energy goes like velocity squared. So if you have two objects with the same mass, and one of them is moving with twice the velocity, then it's going to have 2 times the momentum, but 4 times the kinetic energy, because kinetic energy goes like velocity squared, and momentum goes like velocity. The last thing that I want to cover in this chapter is just the basic definition of power. And all power is just kind of a measure of how fast work is going to be done, and power is going to be work divided by time. So in shorthand, power is going to be work divided by time, and it's going to have a unit of a joule per second, right? Power is going to be equal to work divided by time. We would always expect work to be in joules. We'd always expect time to be in seconds. So a joule per second is also called a watt. So when we talk about power, we're going to talk about how many watts it is, and that's going to be a capital W. Looks kind of like the light bulbs that you buy, right? You're going to buy a 60-watt light bulb. That's just kind of tells you how much energy it uses per unit time. And when we talk about energy, a lot of times it's kilowatt, which is going to be 10 to the third watts. So let's just do a quick little calculation. You climb the stairs in the Science Health Professions building, and it takes you 10 seconds to get to your Physics 101 class. And the next time you're nearly late, but you make it in time. So you climb them in 5 seconds, and is your work the same? And the answer to that is yes. The work you do is going to be equal to your potential energy, which is going to be mass times gravity times height, which does not depend on time. But if you think about it, power is equal to work divided by time. Now, because that number is the same, but this number is halved, you've essentially done twice as much power.